day to you. This is Galactic bringing you space-time. This is the introduction to our Boscovich sequence, which will be running through Christmas. Our intention is to get the solution to two of the greatest paradoxes which have plagued physics for the longest time. The way to get the solution is strictly through geometry, and then the mathematics can be derived. Now, what we need to do is relate space to time. I'm going to show you that that has been done in three ways over the course of the history of physics. The first way you know as lightspeed, and this is a proportion. It looks like a fraction because it's distance over time. That actually would be construed as space over time in terms of a metric. It's linear distance over standard time, which is measured in seconds. And that's arbitrary. It doesn't matter what it is as long as we know what it is, which in this case is the typical second based on the solar year, to just sum it up briefly. So that is the first space-time relation, is lightspeed. The second space-time relation with which we're familiar, or at least physicists are, is space-time. And this is, of course, based on a cubic construction. It's not a direct relationship in the same sense as lightspeed, which is simply distance over time, which I believe is better thought of as distance proportional to time. So those are equivalent statements, and I always do the same thing because it takes me a long time to learn any new trick. Because distance over time is just the way it looks. It's the numerator over the denominator, but that's actually space over time. So that is a definition of lightspeed. Now, space-time is another relationship which is not exactly the same thing as a proportional relationship. It's not denotable as a fraction, although lightspeed is, space-time is not. So what is the relationship? It's orthogonal. And that's a remarkable thing to say. That is the major breakthrough made by Einstein, although you can say a couple of things about what Einstein discovered which are remarkable. But for our purposes, the miraculous insight, because it's a geometric insight, is that time at least can be conceived as orthogonal with space. In the third relationship, which I'll reveal to you now, which is not very well known, but it's resurfacing because it's based on work that was done about 250 years ago, the relationship between space and time demonstrates that time is real. Now, this word real, to use a relativistic term, is relative. The nature of reality is hotly debated now for reasons which I've discussed in prior lectures, but we don't want to get into the philosophical side, although that's very significant, obviously, today. This is actually the solution to all that. To the degree, that is, to the proportion that space is real, time is real. And I'm going to show that to you now. So I'm going to turn on a diagram here. This is the Boscovich force curve, and this is the most famous of his several curves. This is daunting at first. This is directly taken from Boscovich's diagrams in his famous book, Theoria Philosophiae Naturalis, which came out in the 1750s, although it had three major editions, the third of which Boscovich gave his blessing to, but he worked on this for a long time. So what does this diagram show? I'm sorry that I don't have a pointer, but I think you can see that once you just kind of ignore all the letters, it's a relatively simple curve. Now, the vertical line going up from A toward the left, you can see creates a reflection to the left. You can disregard that. What this represents is the relationship between space and time at the atomic level, although Boscovich was not aware of the atom because it hadn't been discovered and would not be discovered for over a century. So what he is actually portraying here is the relationship between two particles. And it turns out that this is the exact equivalent of the nuclear force curve in every sense, and there are three senses to that. So let me show you that. This is the Wikipedia diagram under the article nuclear force. And this is the inner Boscovich curve. And just take a look at that, and I'm going to switch back to the other. You'll see that the inner curve, as it approaches A from the right, you'll see H at the top, and then it dips down below the median line and goes down to F, and then goes up, but it does not do what the other curves to the right do, which is oscillate. Instead, it goes asymptotic to the vertical line A. This is the transition from space to time. I discovered that. Boscovich could not know that, but it is just absolutely incredible that this man understood the force balance system of the universe. And that is not fully comprehended even to this day, but I can tell you that what you're looking at here is a force balance diagram of an atom. And each one of the up-down curves, which you can count 3, correct? Until it goes asymptotic vertically from F to D, such that it's asymptotic with a vertical line AB going up. That is actually the force axis. According to Boscovich's force balance diagram, that's what this is. But I'm going to show you that that vertical axis is actually the time domain. And that makes it just as real as space. And here's how to interpret this diagram. I'm now going to switch back to the inner curve, and this is the Boscovich force curve from H to F to D, although it's actually from the far right. You'll see where it says C over V. These are just points, one on the median line and one on the time-space line. That curved line is the time-space trajectory of, we could say, either a proton or an electron, but in this case, this is the electron. And this is, of course, the construction of an atom, because electrons make shells. Each one of those curves represents a shell in the atom, and the inner curve is the innermost shell of an electronic protonic system. That is known. It is not highly publicized, although you can find out documents online where physicists know this. But it's not well received because the forum in science is not receptive to this kind of information, because it goes against, I'll just say, policy. And that's very unfortunate. It's a human thing. It has nothing directly to do with science, but you are looking at what science actually knows right now. So to switch back to this is the innermost curve, and you can think of the light blue line, which dips and then goes up, as the space-time trajectory of an electron on approach to a proton. So I'm just going to turn this off for a moment. As an electron comes in, think of this as the proton over here, and the electron is approaching it. You know it will go directly toward the proton without requiring any impetal force. In other words, if it were at rest an arbitrary distance this way, and the proton is here, it will start moving towards the proton. Now, what it does when it approaches the proton, it accelerates according to the inverse square law. It's being pulled by the same force that we think of as gravity. It's centripetal force, and this actually is gravity, although since that hasn't been proved, no one says it. But obviously it is, because gravity is simply integral protonic centripetal force. That is obvious. So the grand unification theory, by the way, would be the proof of that. And this is going to be the proof in geometric form, which is the way to understand anything in science. So the electron is accelerating. And now that is shown on the graph as the dip. And it's actually the proton-to-proton relation, so this would be deceleration. But in the case of the electron, you have to interpret this as acceleration. So this shows that the electron is accelerating towards the proton, but the acceleration is shown as the dip. So I hope you understand that. That's rather simple, I hope. So the electron is approaching on a direct line, but it's accelerating, and the median line would not reveal that. You would have to have something moving. And since this is a static diagram, we can show the motion as this would be repelling. In other words, it would be decelerating if the curve went up, but it's accelerating, so it goes down. Now what happens that's magical is when it reaches about the 1 femtometer range, which is the range of the protonic core, inside of which electrons never go. So why does it not go right into the proton? It's because of a force balance relationship. So at this range it's pulled in, but as it reaches the 1 femtometer range, it's accelerating, and now it decelerates. So going up is deceleration. Let me show that again. The way to describe this in geometric language is that the electron is coming in on an asymptotic curve from linear infinity, linear spatial infinity. Off to the right is linear spatial infinity. That blue line never was in contact with the median line. It's a symbolic line showing no force. So the fact that the blue line always is somewhere below the median line shows that the electron is always being attracted to the proton all the way to infinity. And you may recognize this as Zeno's arrow. Zeno's arrow paradox. This is the solution to Zeno's arrow paradox, as well as the solution to the relationship between time and space at the quantum limit. The quantum is depicted on this graph. It is the area roughly, and again I wish I had a pointer, but you can see that right in the middle of this diagram, where the line is not asymptotic in either direction but is transitioning, that transition range is the quantum that cannot be measured as such because it's curved, and the limit of our measuring ability is depicted on the horizontal line. We only can measure linear change at this limit. This is the transition between two domains. The electron comes in on the space domain, but it's being affected by the time domain, and that's why it's accelerating the downward. I know this is counterintuitive, but that downward slope as the electron comes in from the right is showing acceleration. And then the force changes. And this is the secret of atomic physics. This is not the curve that Boscovich drew, but it's exactly the same curve. And what he was describing was the relationship between two arbitrary particles at contact, and his assertion, according to his approach to physics, is that continuity cannot be violated. And so the transfer of energy cannot be in a quantum, and that diagram proves it, and that's 14 minutes. Thank you for staying tuned. This is simply the introduction, so you have some idea of the relationship between space and time at the cutting edge of science, which now you're there and no other physicist is. So I hope you appreciate where we're going. This will lead. Stay tuned. This is Intergalactic.